emergency drives, which have become very popular lately. We make compressors and the new turbo core. Some of you probably have heard about it or seen it. They have no bearings in them. It's all magnetic. So they're extremely quiet in the machine and you can hardly hear the chillers running. Very, very energy efficient. We're into district heating equipment for energy savings. And then we're the heating division. Where it says Danfoss Development down here, those are companies that are for sale. So they develop them for sale. Okay, enough about Danfoss. What sets all of us apart with the stuff that we make here, everything we make is patented. Everything is about 5 to 10 years ahead of our competition. Now that's not to say we don't have competition. We have a lot of competition. In the pressure independent field, there are a lot of people who are getting into it. There's an awful lot of misnomer, misdefinition going on in this business. So I'm going to try and clear that up too a little bit as we get going. We do not sell to OEMs. We don't sell to wholesalers. We sell strictly through engineered reps in North and South America and direct in Europe, Asia, and Africa. We also have a 65% market share globally. None of it really in North America yet. This is a startup in North America. We really started it just about a year ago. Though they had been in here before about 4 years ago and tried to set up a European distribution. But this product has to be sold through people or through rep firms that can help do the engineering and make sure they're right. Okay, now, here's where we get into some of the basics. The first thing is you have to realize that what we're trying to do today in today's world to save energy is to have total flow control. And that's just what we mean here. We mean total flow control. We don't mean, it runs and then we're going to cycle things, right? To get total flow control, you have to have a couple of things. First, you have to have a very stable system. And that stable system is given to you by the control system, thermostats, valves, etc. Then the other thing is you've got to prevent excess flow. If you don't have it, if you have excess flow in the system, you're not going to be able to put the system under control. Interestingly enough, that's balance. It's a balance device. So, basic truth from ASHRAE is that if you have a good balancing system, the reduction in pump costs will pay for balancing. Control valves. How many of you guys in here familiar with authority? Does anybody in here know what the term authority is? Before? Remember that from college? I hope. No? Oh, God. Well, ASHRAE tells the control guys who traditionally have been the people who size and put in the temperature control valves. Traditionally, ASHRAE says you need to have valve authority between 25 and 50% of the pressures. Well, this is interesting. What valve authority is, if you have a butterfly valve and you open it up 10%, how much flow do you get through? It's actually a little higher than that. It's more like 80. Right? And that means that the valve has no authority over what the flow is. And why is that? It's because there's no pressure drop in the valve. Pressure drop means control. It's not just something you put in together for pumps. It means if you don't have pressure drop, you don't have control. And a butterfly valve, when you open it up, there's no pressure drop. It's just like, a hose. Okay? So, what this is authority is trying to squeeze it down so that when you have 10% open, you get 10% flow. And that's why everybody in the control business talks about the turn down of their valve. Our valves at Danfoss are turned down 250 to 1. Right? But that also depends on the actuator, and we'll get into that in a minute. You have to have a good actuator on it just can't get it. You don't have enough room to move it. You only have 90 degrees to turn the darn thing. All right? Let's see what authority really is. It's a ratio of the delta, the pressure drop across a wide open valve to the pressure drop across a closed valve. That's the definition. What does it really mean? Right? Here's the algorithm. And of course we want it to have over 50%. Now, let's take an example. If I have a pressure coming into my branch, 45 feet, and you know, we can call this in feet or we put it in pounds, however we want to do it. If we're pump guys in here, we'll do it in feet. All right? Well, let's just call it pounds, because this really has nothing to do with its ratios, all right? So we have 45 pounds coming out. Whoops. 45 pounds coming out. We have 20 pounds coming back. So obviously, our branch pressure drop is 25 something pounds, feet, whatever. In traditional valve theory, you match the pressure drop on the control valve to the coil, both of which would be 7 and 7. All right? Notice this. This is your balancing device right here. And it's soaking up the difference. But if we do the ratio, we have 25 across 7, divide 7 by 25, we get 28%. By ASHRAE standards, this will be in control and the valve has authority. Right? That's ASHRAE standard. Right. Go to the next example. We're just going to change the pressure because the pump's ramped up or a bunch of stuff closed up there. And now we have 60 pounds coming in, 20 pounds going back, 7 pounds on the valve, matched it to the coil. Let's put 7 over the difference of 40 now. And we get 18. By definition, we are not in control anymore. We do not have enough authority for the control valve to be in control. What I find interesting in this is where's the other 26 pounds? Right there. Soaked up by the balancing device. Now something to remember in this, and I'm going to say it, is a lot of times people don't realize that when you have high limit balancing, see at this stage right here, that control valve is not in control of anything. And so it becomes on-off. When you go above the balancing valve, when you get the pressures up so high on the balancing valve that the flow is maxed out, your balancing, your control valve now becomes two position. Now, that is 99% a true statement. There is the 2% when you finally get down to the very bottom, you might get to control it just a little bit. Right? But your control valve's out of control when your high limit's in control. And we can show you this on the demo on the other side if you want to see it. Okay. Next basic truth. Obviously, if you have too big a balancing valve pressure drop, it's going to affect the way the coil and the control valves work. So, pretty big obvious. Is everybody clear on what this authority thing is? It's really kind of important as we get into this, because what we're going to be talking about now is systems, not components. This is something I like to throw up in almost any one of these discussions. ASHRAE did a survey, or actually an experiment, one of their things a few years ago. And it was really because, you know, it's the old saying, I got an office over here, it's hot, the secretary calls up, sends a guy up from maintenance, and he opens the valve of the balancing valve, and he opens it wide open. And theoretically, she gets cool, right? And the phone call stops. Well, interestingly enough, in ASHRAE's study, that what they came up with is getting flows increased 200%. You only get 6% more heat exchange. So now you're talking about a lot of money to make that extra 200% flow, and you're not getting a good flow. So it's kind of, I like to put that in just because it's double struck. Interesting. Okay, hydronic system balancing. Remember we said the two things, stability and balancing. Balancing is so we don't overflow anything. What is balancing? Well, balancing a system is to limit the flow to every branch, all right, to make it flow the right amount of water. Very simple statement. I want to make sure the water goes over there and all around the road, right? No big deal. All right? Trouble with it is, it's very, very difficult to get this. All right? There are all kinds of different ways of doing it. Annual balancing systems. First one, this is the traditional balancing method where we put a bunch of balancing valves out there on every coil. You're going to have 1 or 2 or 3 valves on every coil, depending on whether you have a 3-way, a 2-way, what have you. And possibly on all of your risers and any of your main branches. And the theory behind it, I'm sure you guys all know, your balancing guy goes out and he's got this drawing that says, I'm going to have this load, or I'm going to have this flow on this coil, and he tries to match it, right? Now let's discuss for a minute where these flows came from. Is there anybody in here who's a consultant engineer, by the way? Okay, hey, great. When you guys design buildings and building loads, what do you design for? Worst case? Did I hear worst case? Or did I hear peak load? Same thing, right? Close. Okay, you design the thing for peak load, or worst case. When you do that, you also design all the flows and all the equipment for that, do you not? Right? So now, you hand this thing out, and if you put a manual balancing system in, you got everything laid out, this coil gets so much flow, this gets this, this gets this. And all the balancing valves are in, and you hand it to the balancing guy, right? He goes around that building, he comes in, and he hits the button, and then he moves everything wide open. Full blast. Why does he do that? Well, because that's what you designed. For peak load, you've got to have everything working, right? So he goes in, and he opens everything wide open, pumps full on, gets rid of the freak drives, the whole bit. And he goes around, balances that system. Get the flow where you want it. You'll go around 3, 4, 5, 6, 10 times. Who knows? And he's making out that report the whole time. Of course, when you get the report, you might be a little suspect, right? Because it looks just like your darn drawing. Right? Looks like the schedule you gave him. Of course, that's what you wanted. Right? So now the balancing guy's done his job. And he's got the report ready. And he says, oh, it's time to go home. And he goes over and he hits the AOA switch, and it goes on automatic. Now, how much of the time, I'm going to ask all our engineer friends, what is the percentage of the time that building really is at peak load?
A few hours, 12 hours per year.
10, 12 hours per year. This year's been a little different, though. I think most people will tell you it's been about 4 weeks, maybe more. Where I live in Kansas, it's a lot longer. It's hot out. All right, so now we have a building designed for a peak that's only going to be a few days a year. Actually, the chiller guys usually say 1 or 2% of the year, right? And when he put the thing on automatic, if it wasn't a peak load day out there, now we're in what situation? We drop back to what's called partial load, right? All right, now when we're in partial load, are we in balance? How could we be? If you're in partial load and you balance the building at peak load, you have fixed orifices out there that are the balancing devices. Let's see, when you have a fixed orifice like a hose, and you push water through, if you raise the pressure on the water, what happens to the flow? It's got to go up. And vice versa. A fixed orifice, and the flow's got to go down if the pressures go down. Right? Well, that's interesting because when I took this thing off of peak load and I put it into partial load, theoretically anyway, all the flow went down. So my balancing valves are doing absolutely nothing. except adding some sort of a pressure drop. That's all it's doing, adding a pressure drop into your system. All right, so if we all agree that that's true, what happens here is as the pumps go up and down, we only go into balance in that building when we're at peak load. When we're at peak load. Now, obviously, the control valves are going to go. And if the control valves are going, but the things are going up and down and the flow's going up or down, what situation does that create? It creates what's known as hunting. Because if the flow goes up, even though the balancing valve's in there, but you're not at peak, that means that the flow's going to go up through the coil. When the flow goes up in the coil, the heat transfer of the coil goes down. Right? When the heat transfer goes down, the thermostat's over here, and it's going, oh my goodness, I need more cooling. So now it tries to open the valve up farther. Before you know it, the pressures change again, and we get this hunting situation going on because of the water pressures within the system. Does everybody see this? Looking out, you're trying to judge faces. I really am. I'm sorry. I know you're not supposed to do that in a meeting like this, but I'm trying to judge if everybody. You know, I see everybody's thinking. I don't think I'm boring anybody. I hope not. But you know, you got to think about this because it's what happens in these buildings. They're alive.
What I don't know. What did you just say that when the flow goes up, the heat transfer goes down?
Yes. When the flow goes up, the heat transfer goes down. If the BTU stays the same. If the load in the room stays the same, the BTUs, and I'll show you that here. Okay, I'll do it for you. All right. One of the things that I like to make sure everybody realizes in manual balancing systems, VFDs. People for a long time now have been talking about VFDs being the be-all and end-all of energy management and pumping and chillers and fans and all that. And they do a heck of a lot of good. But in a hydronic system with a manual balance on it, your system is not stable. You only get about a 30% effectiveness with a variable frequency drive. Personally, my advice is you got manual bombardment frequency drive, just 20 down tubes. Okay? All right. Automatic flow limit balancing. This is one that kind of comes up a lot with me. Some of you guys don't know me from days gone by, others don't. I came out of Griswold and was hired by Danfoss to do this, and I'm glad I left. But manual, flow limit, high limit flow balancing devices were invented 50 years ago or so by David Griswold. The story goes that he got mad at his father, was looking for his father, went home, cleaned the swimming pool in California, back flushed the filter, and the pump shot through a lot of pressure and all the sand went into the pool. And so he got PO'd and he invented what was then the first automatic flow cartridge. It was for swimming pool pumps and it got graduated into buildings. Right? And what these devices do is they have an orifice in them of one sort or another that can be varied. So that when the pressure changes in the building or in the flow, the water system, the device varies an orifice. So you don't have a fixed orifice, you have a variable orifice. Right? And it will hold the flow to the maximum or a high limit as long as you're within the pressure range of the device. That's a very important thing because what flow limiters do is they limit the flow to a maximum. Like if the flow is 10 GPM, I put a 10 GPM flow limiter on it as long as you are within the pressure range of the device, which may be 2 to 32, 4 to 57, and on and on. It just depends on the springs that you have, etc. Now there are lots of varieties of these things. There are can types. There's what they know used to be high flow types, which are kind of look like a stick with a piece of round metal on the top that goes up and down. I mean, there's as many as there are guys who make it. The darn things all work. I've never seen one that didn't work that was engineer problem. But again, it only sets a maximum flow. Now, how does it balance the system automatically? Because they're also called automatic balance valves. Well, obviously, if the flow is maxed at 10, and if flow goes up to 10 and what's in that range, the back pressure coming off of it balances the building. It forces the water to go out of branches in the building. So it works. They work great, as a matter of fact. I don't really care whose it is. But the problem with them is that it's only at that high limit. Right? So it does nothing. If you're not at that high limit, it's not going to do anything. Right? You can vary the pressure all you want, but if the flow doesn't go to the high limit, it's not doing anything. But once it's at the high limit, it's in control. Not the valve, not the control valve. The control valve becomes two position at that point. All right. Interestingly enough, these things are really cool because they do one thing that's really neat. They make your freak drives work. If you put a high limit device in here, it cuts, if you want to think of it like a sine wave, it cuts off that top piece of the sine wave with the flow because it's a maximum flow. And because of that, that stabilizes the system a whole lot better. And you can get about 70% or more effectiveness out of your frequency drives. It depends on how you're putting them together and various other things. So that's really, that's really about what automatic balancing is. Okay, we all clear on that? That's the basics.
What do you mean by 70% effectiveness?
Ah, good question. The problem with frequency drives is that they require a real stable up, a real stable down. And if you don't have a real stable up, real stable down, or a stable system going, the frequency drive actually begins to hunt. Right? It will start to hunt for position. That's why it won't work on a manual. It's hunting at the same time the thermostat's hunting and the whole bit. We're cutting off the high end with this, so now we know that it's going to work somewhat, but when we're not at high flow, we basically have the same situation as we do with a manual system. So if for some odd reason the system starts oscillating out there because things are opening and closing or the valves are hunting, the pressure stats that you use for the VFD will also make it react, and it also gets unstable. But 70% of the time it's going to be perfect, and it saves a lot of money. Right? So that's why they say its effectiveness is about 70%. In a manual situation, basically you can have the frequency drive actually contribute to hunting within the system. Because as this thing's hunting for position over here, the frequency drive is now hunting for position. So as it hunts, the whole thing goes out of whack. Okay, so that's really what's meant by it. Hope that's a good explanation. Now we know. All right, pressure independent temperature control valves. There's a lot of definitions on this right now. But the official definition by all the guys that make it, which I think is, I think it's as good as any. What pressure independent temperature control valves are valves which do not allow a change in the flow rate. When the pressure differential across the valve changes, but the load does not. Okay. This is a very important thing right now. So what these valves are, is you got a valve in here, it's got, let's say, a thermostat on the wall. You got a load in this room. Load in here stays the same. Pressure in the system changes. The valve does not change or move. There's no hunting. Okay? Does everybody see that? Very interesting thing, because how are you going to do this? All right. Only a change in the load will cause a change in the flow rate. Why? Because we're going to move the valve to match the load, so therefore the flow matches the load. Right. Down at the bottom here is something kind of interesting. This pressure independent ATC valves dynamically balance the system. We'll go back into that again in a couple of seconds. But what that really means is that it will balance the entire building to the various loads within the building. It's not high, it's not manual, all the time, dynamically balances the building. All right, let's start off with what are these valves? This is where I said I'll try and show you guys how these valves work. This is the standard flow calculation. Flow equals CV times the square root of delta P. If you want to change it around to CVs, which everybody uses the size, whether it be balancing valves or control valves today, standard control valve, CV is equal to the flow divided by the square root of the pressure drop. Okay. And what we said back there by definition is that, you know, these are valves that any pressure change within the system does not affect the flow. And in fact, what we do is we make the valves basically have two components. The first component is the temperature control valve. The second component is a pressure regulator. Now, that pressure regulator, in this case, is used to regulate the differential pressure across the valve and hold it to a constant at all times. Now, what is this regulator? Well, it's the same as a regulator you might have on the gas line at your house. You know, the big gray thing that looks like a circle on the side there? The gas is coming up through the main lines. It's going to run to your, running up the subdivision or whatever it is you're living in, and it's going to be out there 200 pounds. And you're not going to pump 200-pound gas in your house. You're going to pump in 6-pound, 10-pound, whatever the rate it is here. Well, you've got this regulator sitting on here that's going to regulate, no matter what that pressure, the main pressure coming is only going to allow 6, 10 pounds or whatever it's sent for to come into your house. And that's very important. Well, we're doing the same thing. We're doing it with a pressure regulator that's in the bottom of this valve. Okay? So we're regulating the pressure to a constant. Now, when we regulate the pressure to the constant, that means that the delta P here is a constant. Now let's look at this thing from a mathematical standpoint. This is a constant. And by the way, if you're putting in your heads, a Danfoss valve, everything up to a 1.5 inch is 3 pounds is the constant. Everything over 1.5 up through 10 inch is 4 pounds. Alright, so that's what you use when you're cycling pounds. Alright, let's just say that we could do this with 3 pounds and then we figure it out, but let's just use it and say constant is 1. So we're going to say this is 1 pound right here. So now, flow is equal to CV times the square root of 1. Square root of 1 is 1. Flow is equal to CV. Make sense? You go out there to size a valve today and you look at the CVs, right? Not any longer. Now you look at the GPM. And with Danfoss, anyway, we don't downsize our valves at all because we don't need any extra pressure changes based on the equipment that's within the valve, the differentials. So ours are all line size. So all we want from you all is the line size and the GPM. And if it fits in the range, you got it. Okay, it's pretty simple stuff. All right, is this clear as mud to everybody now? That's where all this came from.
Other than you're using 1 as the default.
We could put 3. It doesn't make any difference. We could put 3. We could put 4. What it is now the manufacturer, when he sizes the valves, when he puts, when he's building the valve in there, he now can set whatever default he wants, and that'll give you the flow. So you can look it up. The flow, let's say the flow is 10 GPM, right? And he sized it to have a differential pressure of 3 or 4, whatever the standard is. So that's, and this is the way they do it. So the CV is always going to be equal to the GPM based on the charts. Make sense? We don't care what the constant is. It's constant. Okay? Manufacturer of the valve will figure out the constant versus the field. Quite frankly, it's a whole lot more complicated than we have. This is trying. Yes, sir.
So on my flow program, now instead of doing CVs and valves, you know, like we put in the DPA, we put in the delta B, just so it's on my control.
You don't even bother with the delta P. You just say, I want the flow.
Oh, yeah, the delta B.
No, you don't. You can if you want, but you don't need to. The only thing you need to know is the delta P is going to be this for this many valves,
Yeah.
and that's so I size my pump to be this. That's all you need. Okay? That's a good question, but it's a mathematical thing that's done by the manufacturer when they size the valves. That's the only explain.
I was just going by your saying your charts are 3, doing the math doesn't come out the same. I agree with you.
Yeah.
It's all maths, but
Yeah, no, I know.
You're
But
saying you're trying to
it's-
pick-
the math right now is, for example, as opposed to, I can sit down and show you the charts, if you want, right? But this is true of everybody. I'm not just talking about the Frost when I talk about this. This is how these valves work. Period. You're using a differential pressure regulator to regulate the pressure to some constant. And when you do it to a constant, that means that you can make the CV and the flow match. Understand how you do it. Okay. How do these valves actually save your clients money? And how can you make use of it? I'm sure most of you guys have seen these things, and today we got the variable pumps, etc. And I'm sure you've seen these charts. This is kW per ton, and this is the percent of load. Right. Percent of load with chillers and boilers is generally thought to be the delta T. Because you have the delta T, you're trying to heat the water up, or you're trying to cool the water down. And the delta T's will match the percentages of load. So, if you guys go out to specify a chiller, you might specify a chiller that's what, 15-degree delta T at 80% load. Seem right? So that would be right out here. We would call that a 15-degree delta T. All right? But when we sized it for peak load. So in sizing it for peak load now, the only time we can get to here, basically, is at peak load. Now we're at partial load. What is the normal delta T you guys have been seeing in the field around here? You know, I mean, go in and look at a machine when you see it, 10? See it
10,
5?
12.
Been seeing that much? 12? Really? That's pretty good system for some. Usually we see, like at a hotel complex like this, we usually see 2. And in hospitals, we've been seeing, depending on how we do it, about 5 to 6. Universities, they're terrible. They're terrible. They get so many bridge networks and all that kind of stuff. It could be 8, it could be 6, it could be 3. Who knows? But wherever it is, it's going to be someplace down here in the lower lows. So let's just, for the sake of argument, say at 15, half of that would be 7, and that would be about 40% load right here. Right? So now I have 40% load, and it's going to read at about 6.64 or so, 63 kW per ton, as opposed to, if we were down here, about 0.53. Doesn't sound like much, but it's per ton, and it's kW hours. Okay? Now, what we want to do is we want to get this thing to be out here as much as we possibly can in the range, the most best range. So how do you do it? Okay, let's go back. We said we were going to talk about the heat exchange formula just a little bit. This is where all the systems This is a standard heat exchange formula for water. BTUs equal to 500 times the GPM times the log mean temperature difference. And I think I'm the only one in here that's old enough to remember that you do that on the back of the slide. So it means I can't do it anymore. It's not on a calculator. I'm not spending like my kids $100 on a calculator. So let's look at how this formula is made. There's other things that go in this formula, by the way. I mean, we can argue the formula. We're ready to with anybody who wants to. But this is the basic heat exchange formula. BTUs, 500 times GPM times delta T. Okay, and the 500 times GPM is considered flow because that's your conversion of pounds per hour. Right? Pounds per hour. And the delta T. So now, the formula simplifies down to load is equal to flow times delta T. And delta T, as we just said, is the loading on the chillers or the boilers. So that's your heat exchange. How much heat did you absorb out in the space, right? Pretty simple stuff. So now, if my load, right, if my flow goes up right here, but my load is constant, what happens to my delta T? If my load, let's say this load is 24,000 BTUs, and my flow, which was maybe 4 GPM, now goes to 6. What happens to the delta T? Got to go down as opposites in the equation, right? And vice versa. So that means if I get a higher flow through the coil, I don't get as much heat exchange. My delta T drops off. Ergo, high limit balancing, or anything else that holds the max flow. Right? That's what it's all about. So that we don't screw around with our loads. Okay, now, this is kind of interesting. We just said that in most systems, at partial load, the delta T goes down because we're partial load, and we see this thing like the 40%, and the price of the power goes up, etc. Right? So what you end up with here is that you want to find a way to have a stable heat transfer. So when you designed the coils, what did you do? Did you match the chillers? If the chiller delta T was 15 for cooling coil, did you match and said I want a 15-degree delta T cooling coil in space? Is that right?
Sure.
Or maybe you want a little bit higher, depending on the humidity. You know, you can. There's all kinds of games you can play. But if you're at partial load again, that means your flows have got to be different. So naturally, your delta T can't be that high. So here's what we're going to do. We're going to put a valve, a very precise control valve in those coils. It's going to get rid of all the effects out of it. And it's going to create a new high limit balancing point at every position it takes. And there's the secret. What that means now is that the coil itself, this delta T, becomes a constant. It's what we design. So if we design a coil for 15-degree delta T, putting these valves on there, you're going to get a 15-degree delta T. And there are obviously some exceptions, but about 50 to 80% of the time you'll get that 15-degree delta T. And when you do that, you go back to this chart, and even at part load now, we're still going to be loading our chiller someplace in here. Or our boiler, it doesn't make any difference. Just heating water versus cooling water, right? So that's what happens. We want to hold the delta T something higher to match the coil. And when we do that, if the flow goes up, well actually if the load goes up, and the delta T holds the same, the flow's got to go up. And that's how the valves work. The flow matches the load at all times. So, when you get into this, we recommend a few things. You got to be a little careful with people that say this sort of stuff, but industry right now is saying you want your design delta T's and coolant to be someplace between 18 and 26. For those of you who may not have heard about it, the DFW airport job is specified at 24, which I thought was kind of interesting. On the heating side, 40 to 60, I would always recommend that in the condensing boilers, and maybe even higher, but that's what I would recommend. We say fully loads the chillers, the 80-20 rule is because based on peak loads, how much of the time you're in peak load, etc. Okay, so you use less energy to maintain desired environmental conditions. Now why? Delta T's take less flow. So when you're designing a building, you have to sit back now and you have to think about my pumps and my piping, because you don't need as much. In general, most people experience about 30% less flow with these valves. So you'll need 30% less flow in general to do the same amount of heating and cooling work.
What's the general delta T of the design for?
Someplace between 15 and 20. On cooling. On heating would be 50 to 70 or something like that. Okay. This is a new construction stuff. This, of course, minimizes the flow per ton, reduces the pipe sizes, the whole bit. So if you see a job out there that's been specified to go pressure independent, the one thing you don't want is to have it VE'd on you. If it gets VE, now you've got to ask some real interesting questions like how much did you put in for the bigger pipe? All right? You can't VE a pressure independent job and have it work. And there's a lot of people who are trying right now because they don't think the way these things think. All right? You require fewer pumps and less pump horsepower. Okay, operating benefits. The one that I really think is important is this, VFDs. When you put these things in the line, the VFDs now will literally do exactly what you wanted them to do 100%. Their effectiveness is 100% literally. Why? Because the system is slow. The system is operating like it was a heartbeat at rest. Just constantly working the way it's supposed to be. That's right. It's stability. Okay. I'm going to try and show you guys a little bit about what the Danfoss valve has. And again, we said there were two parts to the valve. You have the total valve looks like this in the line. And the first part is this real precise temperature control valve right here. It's a globe valve, right? And it goes up and down and it does this thing. And then we have the second part over here, which is the differential pressure regulating. And what you get here, like in your gas meter, this will be your high pressure. Comes in and it gets right in here. And then we take a low pressure reading right here. So the only moving part you have is a diaphragm, and it controls the pressure, just like a gas pressure regulator. Okay? To a constant. Now this is the whole thing working together. Of course, it's kind of fun to watch, but you'll notice that the stem doesn't move, and that's because we don't have a motor on it, and we don't have a thermostat on it, and it's a little resulting constant. So there it is. Now, there's one other feature that I like to really talk about with Danfoss, which really separates us from everybody else. We make these valves from 1/2 inch through 10 inch, up to about 1,300 GPM. The actuators we put on them are very unique. The actuators are self-learning or self-commissioning. That's kind of a new thing. Remember we said we size our valves to be line size and then the flow to be within it. And you can sit here and say, well, let's say this is a 10 GPM valve. You know, it's the flow on this would be 1 to 10 GPM. And let's say you only need 5 GPM. So you move this to 50%. Now I have a 5 GPM valve. But this doesn't do us any good if the actuator doesn't know that. So these actuators that we have commission themselves. They measure the stems when you first power them up. And it gives you a full signal now for the new flow rate. So if you had 0 to 5 GPM, you would get a 0 to 10 or 4 to 20 signal for that actuator, for the full range.
0 to 5, so
Yep.
put 0 to 5.
That's right. And what makes it more fun is if you make a mistake, and none of us would, in size of pipe and all that, all you have to do is take the actuator off, change the rate up here, the percentage, repower this, hit the reset button, and it now relearns, self-commissions. And you got a little picture here that shows this, just because it's funny. So that's what we'll do. Now the actuator will go on, learn the type of sound. Okay, so what do we got? These things reduce the cost of operating your chillers and boilers by forcing it to work at the sweet spot most of the time. Obviously, the times it won't, but most of the time. You select the valve based on the design GPM, not the CD. You do not put balancing valves in here. Now that brings up the subject I said I would talk about. See, a high limit flow device that we call MAC or automatic balancing device. What that is a single position flow limiter. Yes, it works on a pressure range, so the range may be 2 to 32, but it still is a single flow high limiter. All right? When you put this in and you put this together with a constant differential pressure, what happens is every position the temperature control valve takes in here, the flow cannot go over it. So in essence, you have built in an infinite number of high-limit automatic flow devices. So, because of that, the whole building is constantly balancing itself, dynamically balancing itself, based on the position of each control valve throughout the building. So it's also constantly changing. And this means that your building is being balanced to its load, which is really cool. And I think that's about it. And do I have any other questions? You can't tell me I explained this thing that
I
way.
got a question.
Go for it.
Okay, you said earlier that you just size
Size.
valves are sized for GPM, pumps are sized for what?
I didn't say that. What I said is you need to know the constant delta P for your pump to know the full head you need. Okay?
So you would size then, say you're looking at the worst case for this down the line. You would size that pump for that pressure drop in the pipe, pressure drop across that valve with the sump, plus the pressure drop beneath the coil.
Yes, that's correct. That's all I would do.
Now,
That's it. Now, with these valves, of course, you can also do some other things which I don't like. You can bigger pumps on those. Everything will be made up. These valves work for your system. But your brake drive will bring your pump down to some other level.
I agree.
Yeah.
Okay. Now, you had another flow, another chart that said primary, secondary.
Yes.
Do I take that chart to say that to the chiller you want variable
No.
primary flow?
No.
Does it matter if you have primary, secondary, tertiary, or tertiary loops with these valves?
No. As a matter of fact, there's an existing building working. There's lots of ways of looking at things.
Well, that's
Let me-
the issue with
Yeah.
working on the project.
Okay. If you were to have, let's say you have a central plant.
Exactly.
Okay, a central plant. And I got a loop on it. And I got 20 volts.
Is the loop for the chiller for the primary or just one loop?
Just a single primary
Single.
Okay? Now, I can put one valve in every building.
Sure.
The way these valves work is that when you put a valve on the return line of the zone piping system, okay, you have made that range completely independent. It's pressure independent now of everything else. Okay? So, what that means is the building's now independent. that's going to give you X amount of savings, right? And it will assure your delta T coming back to the plant. Right? Now, that's only going to give you a portion of the savings. So now, when you get into this, you also have primary, secondary, tertiary, quaternary, etc. systems. The more you do, the more you save. But there becomes a limit. You know, these are nice little valves, and if you want to put them on a VAV box, that's great. They won't weight you down. VAV box will reheat. Huh? Dude, I could give you an arm thing. So if I got a little two-position valve and a high limit on a VAV box, right, which is 1 or half of 1 gallon a minute or something, now I want to circuit it so that maybe I got 20 of them on the same loop and I put 1 valve on that loop. Now I'll get about 90% of the effectiveness that I would have had, but I've got it for 20 GPM or whatever I've got. How you do this with the controls is pretty simple. You have to have a delta T stat, supply return, bearing in mind that these valves are going to lower the flow to the lowest possible amount for BTUs. Now that's an interesting problem because let's say out of the 20, 19 boxes shut down. But I still got 1. And this thing is trying to lower the flow and lower the flow and lower the flow. So I need a little pressure control that resets my flow. It's going to reset that delta T. And the whole reason behind that is I don't want to start at 1 box that still needs something. So you have to think a little bit like that. If you have an automation system, it's really easy to do because you're just adding a point here or there. But in the case of the other type of things, that's really not very difficult either. You just need to buy the right differential temperature control. So you can start adding these things up and adding things up. Generally speaking, if you really want an effective system, what I've been recommending lately is 1 on the building, or 1 on each of the big areas. Now I'm going to get quite a bit of the savings are going to come back to me, where the rest of it's not going to make a whole lot of difference. The big valve is going to pick up that extra pressure differential, extra temperature differential. Does that answer your question? I don't know. I'd have to almost sit down with a piece of paper, draw this whole thing out. I did it for a guy at a lab in Chicago the other day, and it got real complicated because he also had process stuff. So when you get process, that's any other questions? I got a question for you. Can I sell you some of this stuff? Huh? Please? Can I get an order? An order, please? Thank you all for coming. Appreciate it very, very much. Somebody else